There I said
No, sir.
nobody is there. Okay.
Currently, nobody is.
Okay. Okay. Anyway, they may be able to download it and see.
YouTube पे live
You will like
recorded.
नॉर्मल तो रहता है
हाँ
नॉर्मल तो पार्टिसिपेट रहता है
Are they are aware ना sir today lecture?
या
Okay.
वी आर लेट दैट्स व्हाट
नहीं से कोई आया नहीं
अब देखा था
कोई नहीं आया था
देखा ही नहीं क्या कोई लिंक तो भेजा गया है
Okay. I'll start now.
हाँ सर
and last day also I told na the meeting is class is there
हाँ
So after maybe 5 minutes, I will change to the original presentation. This I will just clear.
all right
Okay. So good evening everybody. So today we will be discussing initially some clarifications or doubts raised by our colleague Tapas. So let us discuss it maybe another 5-10 minutes, and I will discuss briefly about the NMR, solid state NMR, something which we have not discussed previously on quadrupolar nucleus. Some very basic aspect we will discuss. Okay. So Tapas has asked one question: what is the meaning of white background elements in the periodic table actually, like argon, technetium, etc. Actually, these nuclei, either their spin is equal to 0 or no NMR is possible with such type of nuclei. For example, francium, radon, etc. Some of them are radioactive also. Some of them are I is equal to 0 and no NMR. So far, if you see in the literature also, you cannot give. For example, argon NMR, I don't think you can find in the literature. At least I have searched the literature, we cannot find. Similarly, polonium, these are radioactive, so we cannot see. So some of them like actinide elements like americium, curium, berkelium, etc. They are really radioactive and they are not possible to do NMR. Of course, people have not tried also, you cannot find also in the literature. Some of the isotopes are no NMR active, but due to this radioactivity we cannot do. But otherwise, most of the nuclei which are shaded with orange color as well as those shaded with blue color or cyan color, we can do NMR. So hope your doubt is clear. So white background means so far nobody has recorded NMR for using such nucleus. Let us go further. And that goes to the second question. That is what I have written the answer. I have made you the answer. White background represents the NMR experiment cannot be performed with this nuclei due to either lack of stability of the isotope or radioactive nature or I is equal to 0, etc. Let us move further. And the second question you were asking was about why. That's a good question actually. Why? See, if it is a cos theta term is there in the, for example, if you see the expression, there is a cos theta term in the peg doublet. And cos theta term is 90, when the cos 90 is 0, so you should not get a maximum there. But remember that this overlaps or this is convoluted with the Gaussian line shape. Gaussian line shape, and also there is a one, why this is moving? Let me check one. Okay, that's good.
I make the I change this slide. Continue.
Okay. Let me see. But not moving. Okay. Okay, now it is moving. So if you see the intensity of the peak results from the sin theta weighing of the spectrum, there is a, in addition to the cos theta, there is also a part which is coming here. Sin theta part also is there. So that is why exactly at 90 degree you will not get the 0. There is a sin theta because cos squared theta is cos 0. So 1 into 3, 1 will remain there. So 3 cos squared theta will become 0 because cos squared 90, cos of 90 is 0, cos squared 90 is 0. Again 3 into 0 is 0. So 1 into sin theta term will come. So this will give some number. So other terms are also there. So that is why you will get a maximum there. So this document also I have also mailed you one document. So probably you can see that document in the page number 70. Now the third question is that explain how can we know 10% aluminium is best for making glass ceramics. Though we get 5 signals, how can we know about the specific 5 layered structural information from this data? So if you see here in the NMR spectrum, what happens the moment you go to around 12, in between 10 and 12 if you see now, in between 10 and 12 if you see the for 10% doped sample or 10 mole % containing sample, all the 5 peaks 1, 2, 3, 4, 5 are literally we can very clearly see, well distinct peaks are seen. And also if you see one more thing, there is some small peak here. If you see in the other two cases, the extreme cases, the sharp peak here is there. This is due to an alumino-silicate with all aluminium as next nearest neighbors around silicon. So these intensities are quite high. Only 10% and 12% if you see, there is an amorphous component is also there. There is a background and there is a crystalline component is also there. And among the 10 and 12, if you see, the 10% is having, if you see, having a more crystalline component. So if you see the properties, 10 and 12 will have almost equivalent properties, and out of this 10 will have improved properties because and you can, the crystalline phase, you can very clearly see that the contribution of the crystalline phase, very clearly you can see. And how this gives machinability, because from this NMR alone you will not be able to see, you have to do XRD also. Once you do XRD and then combine with the NMR results, then you will get idea what is the structure or what is the origin of these 5 peaks. The peaks in at minus 92, minus 88, minus 75 and minus 80, some 83 points. So these peaks now, these are almost a fixed. 92 is coming to 88 and 88 is coming to 83. And then it is coming 75, etc. Correct, now 79, 75, etc. So that means there's a systematic shift in the silicon environment, and that is only possible with we have this type of that aluminosilicate structure. So hope you understood this structure. Why do we have 2 signals for silicon 4? This is nothing but once the 2 different crystallographically different silicons are there. If you see the crystal structure or triclinic phase of CaSi2O5. In fact, triclinic phase is the most distorted phase of calcium silicate. So here, all silicon atoms are distorted. Multiple silicons are there. And in fact, even a tetrahedral silicon, we have 2 different crystallographically different silicon. That is why we get 2 peaks. So this is a straightforward thing. We will be able to understand this. Then it's a very nice good questions. What is the reason that during random distribution with titanium, the central tin is not replaced? Only the 10N are replaced. In fact, see, crystallographically, there is no difference between the central atom and the corner atom because crystals are having a property called translation. At some point of time, the corner atom can become central atom and the central atom can become corner atom and the vice versa. So due to this translational symmetry, corner atom can become central atom and central atom can become corner atom. So it is necessary to take either central atom or corner atom because crystallographically these positions are same. So if you take corner atom, it is equivalent to taking a central atom only, or if you take central atom, it is equivalent to taking a corner atom because they are crystallographically same only. The corner atom can become a central atom and central atom can become a corner atom due to translation symmetry. So crystal has this property. So for ease of consideration, because we are trying to probe tin, so that is why we have taken it as a tin at the body center. In fact, you can take it as a tin at the corner also. If you see that also, the results will be same because number of next near neighbor will be same. So that is what I have written here. Central TA can also be replaced, but remember that we are probing the 119 nucleus. Then we have to probe with the titanium. If you want to put titanium at the center, then we have to probe with the titanium NMR. Due to translational symmetry in crystal, body center atom can become corner atom and corner atom can become body center atom. So they are one and the same only, corner atom as well as the body center atom. Then the another question asked is that, please explain the significance of these 4 parameters. Very good. So I don't know this probably today once again I will explain to you in the class, or just remember that see solids the moment we start spinning, we get number of side bands. Is it not? Number of side bands you will get an isotropic peak and you will get number of side bands. And from the side band intensity, you can calculate parameters like delta 11, delta 22, delta 33. Remember, sometimes in text they write delta 11 is equal to sigma 11. Delta 22 is equal to sigma 22. They interchangeably they use in many textbooks. They replace delta 11 as a sigma 11 and delta 2 is a sigma 22 and delta 33 is a sigma 33. Don't worry about that. They are one and the same only because they are components of the chemical shift anisotropy. Instead of delta iso, people write sigma iso. What is iso value? Isotropic is nothing but if you have a matrix now, because chemical shift you know, or I have explained in the previous class, it is a second order, second rank, not second order, second rank tensor. So second rank tensor means what? We have 3 raised to 2 components, 9 components, which can be represented by a matrix. Is it not? So a matrix is there with 9 components, and one can always diagonalize that matrix. How this diagonalization will happen? When a molecular frame gets converted from the laboratory frame, when a molecular structure or molecular system gets transformed from laboratory frame to principal axis frame, the matrix get diagonalized. So once the matrix get diagonalized, we have only diagonal component, and that is the nothing but delta iso. So delta iso is nothing but 1 by 3 into components. This anyway you can understand, because in matrix, if you sum all the diagonal elements, what you get is nothing but the isotropic components. Then another terminology is also there. So delta II, that is the component can be always expressed with respect to sigma reference minus sigma II. Sometimes the sigma reference is so small, so we can neglect it, and then we can take sigma reference minus sigma II. Or one is very large. One is very large compared to this one, so you can always take delta II is equal to sigma reference minus sigma II. So there is a third parameter called anisotropy parameter. Anisotropy parameter, now by convention, among these 3 components, 1, 1, 2, 2, and 3, 3, 3, 3 will be the largest. Okay, so if you take the difference of 3, 3 and delta iso, then what we get is nothing but the anisotropy parameter. So higher the anisotropy parameter, what happens? Higher will be the electron load. Higher will be the electron load means more electron density is there. So once more electron density is there, then it will be more shielded, de-shielded, and that concept will come. So that is why delta anisotropy is nothing but is measure of the chemical shift anisotropy. So this is the 1, 2, third term, and the fourth term is given by delta 11 minus delta 22 divided by delta 33 minus delta iso. So this is a function. Many times what happen, delta 11 is equal to delta 22. So then we say it's an axially symmetric system. So probably today also I may give, I don't know if I am encountering, I will discuss with you. So when delta 11 is equal to delta 22 is an axially symmetric system, then I don't know whether I have, yeah, I have written here. Now. See, I told now delta 11 can be always correlated with the sigma 11. If delta 11 is equal to delta 22 or sigma 11 is equal to sigma 22, what you have is an axially symmetric system. See, peak here, and then there is a symmetry. There is a, what happened? Only one maxima you see, then you see 2 shoulder. Only one shoulder you see. Here, how many 2 shoulders we are seeing? One maxima and 2 shoulders. This is a shoulder, this is a shoulder, and this is a maxima. But when sigma 11 is equal to sigma 22, only one maxima and one shoulder you will see. So that is why I have written that I shall do it in the next class. So this is what I want to convey to you, that always anisotropy parameter is always expressed with respect to sigma 33 minus sigma iso, and this eta symmetry is given by delta 11 minus delta. If it is 0, then we have a perfectly symmetric system, axially symmetric system. And then another question you have asked is whether the symmetric pattern of barium stannate leads to sharp peak. For example, you can see sharp peak here. Correct now? This is 1419 and these 2 peaks 1417. Because tin is having 2 isotopes and abundance of 119 is more. So that is where you get more peak. So this is nothing but a chemically equal, chemically same, but magnetically equivalent. Very important concept is conveyed here. There are tin with a chemical equivalent and magnetic inequivalence. So your question is, sir, whether the symmetric pattern of barium stannate leads to sharp peak and hence coupling of tin 117 is observed. And the asymmetry in SNO2 leads to broad peak and hence this type of coupling, though there cannot be observed as it is overshadowed by the broadness of or some other, no, you are perfectly right. In the case of tin oxide, what happened? Tin oxide is having an asymmetric system because it's a tetragonal system, whereas barium stannate is a cubic system. So in tin oxide, you can see here, it's a tetragonal system. Na? You see here, it's a tetragonal system. A is equal to B, but not equal to C. No, no, sorry, B is equal to C, but not A. A is not equal to B or C. So this problem is there in SNO2. So SNO2 environment is more asymmetric. So once it is more asymmetric, more broadening will be there, and you are not able to see the coupling between 119 and 117 in the case of pure SNO2. But if you become barium standard, it's a cubic system, highly symmetric system, and you are getting good P. In fact, in SNO2, SN environment is distorted, tetragonally distorted. So that is why we don't see that. So answer is combined effect crystal. Of course, crystallinity also matter and local symmetry also matter here. And another question asked is here the coupling between tin 117 is not observed. Please explain. You have see in the previous case you see here you are able to see the coupling one here, and then another is a very sharp peak. You see the sharp peak of tin 119, and this tin 119 is coupling with the tin 117, and we get to these symmetric doublets. Whereas the moment you go to calcium standard, etc., it is a poor, crystallinity is poor. You see how much broad the line is. The line broadening is quite high. So the splitting or the coupling we are not able to see. This is purely because of this slightly poor, crystallographically poor environment around the tin nucleus. That is why we are not able to see the picture. A doublet form. In fact, you can see this is from minus 550, almost like minus 750 actually. Almost 200 ppm width. Even 200 ppm width you see somewhat broader. Whereas here, let me see how much is the width. This is almost like 80 ppm only width, 640 to 720. Almost 80 ppm. Here you see how much sharp the line is. Whereas even if you here it is almost like a 200 ppm. So here you see the line broadening. So due to this line broadening, we are not able to see the coupling between 119 and, sorry, I made a mistake here. This is 119 tin, 119 tin. Here tin should be written, but I have forgot, right? So this is the 118 mass NMR spectrum, the AV303 structure. This is poor crystallinity, we are not able to see. Let me go further. So that is the answer. Poor crystallinity is the answer. I think I am finished with all your queries. Let us try to discuss some aspects of NMR now. Solid state NMR. Hope the things are clear to you. In case any clarification is required, please feel free to mail me or telephone me. I'll be happy to answer. These are some of the queries raised by one of the participants, Sri Tapas Sahu.
YouTube.
Somebody is there?
YouTube,
Three people are there. Okay, okay.
यूट्यूब में भी है ना, इसमें नहीं होगा, इसमें नहीं है कोई.
Go further, maybe around 190 or something.
In 315 site.
No. We will go around 190, 200 or something, 250 or something. Because this is lecture 12, na? Probably I am somewhere here only. So let us try to discuss a small portion of solid state NMR. Of course, many things are to be taught, but let us try to discuss some important aspects of solid state NMR. So I will just briefly discuss regarding the quadrupole NMR. So normally quadrupole NMR in solution, people may not be doing much quadrupole NMR because many like carbon 13, proton, then phosphorus 31, etc. are already there. So they give good information. And nitrogen 15, these are all spin half nucleus. But in solids now, if you see around 70, around 80% of the periodic table, if you see are quadrupole nucleus only. So in solids, we are very much interested in quadrupolar nucleus NMR. So by convention, I think I have told in the last class, if it is a spherically symmetric, spin is equal to half, there is no difference or no distribution of charge. It's a distribution of charge is symmetric. It's a spherical distribution. Whereas the moment you go to oblate or prolate shape of the prolate nucleus or oblate nucleus, what we see is there is a distribution in the charge and it will generate a quadrupole moment called EQ. EQ is nothing called the electric quadrupole moment of the nucleus. Some people say as Q also, but normally let us say we consider it as EQ. In many textbooks, it is given as EQ. Okay. So by convention, it is by convention only. If EQ is greater than 0, then we say it's a prolate nucleus, and if EQ is less than 0, we say it's an oblate nucleus. These are purely conventions. You need not bother about that. And in fact, you can, there are expressions available for this. For the time being, you forget about all those things. And now let us go to the electric environment around the nucleus, quadrupole nucleus, electric environment around the quadrupole nucleus. You see here, quadrupole nucleus is there. This is a prolate shape, correct? No? So around that, there's an electric field gradient is there. Some regions are positive, some regions are negative. So there's an electric gradient, or there's an inhomogeneity in the electric field. So that is called electric field gradient and given by the expression E into Q. E is charge actually, and what is the Q? The one is the net charge. So as we have discussed in chemical shift anisotropy, this is also a tensor. So in tensor we have 9 components, second rank tensor we have 9 components, and if you consider principal axis system, we have only 3 components, and you can take the trace of that, and then you can calculate the what is the exact value of this isotropic value of the electric field gradient. Now forget about all those things, let us see what are the parameters in quadrupole NMR. The quadrupole NMR, the most important parameter is CQ. This is called the quadrupole coupling constant. So E, is nothing but the charge of the electric field gradient. E is nothing but E, charge of the electron only. And Q is nothing but the charge of the surrounding electric field or the surrounding environment. And Q is nothing but the charge, of the nucleus. And H we know, Planck's constant we know. And one we know, gamma is a parameter called Sternheimer anti-shielding factor. What does it do? What happens when when a quadrupole nucleus is sitting in an electric field gradient? The electric field gradient EQ causes a distortion of the core electrons, because as I mentioned, there's an electric field gradient is there. You see here. So this electric field gradient, which is created by the coordination environment, correct now? We have a trigonal coordination, we have a tetrahedral coordination, we have the square pyramidal configuration, and depending upon the configuration, the electric field gradient will change. So this electric field gradient, if it is highly symmetric, then no problem, it will not distort. But if it is asymmetric, then it will distort the core level orbitals. That is why the magnet.
This is here eta. An equation eta is which one?
This gamma. Eta, eta is the asymmetric parameter. Actually, I should write it as, sorry, I'm very sorry.
Equation.
Eta, I think eta should come here. Eta is coming here. Sorry, I think I should write here. Eta is asymmetric because it is coming from the tensor only. Okay. It is nothing but the V xx minus Vyy divided by Vz. That is nothing but V11 minus V22 divided by V3. Okay. I think. So eta is the asymmetric parameter. This is parameters in quadrupolar NMR. The eta equation is given here. Equation for eta. I think I should write it, otherwise people may get confused. Equation in the previous slide. Equation in previous slide. The equation that is called asymmetric parameter, and that is here, that is coming from here only, V11 minus V22 divided by VT3. When eta is equal to 0, FG is actually symmetric. Same thing valid for chemical shift anisotropy also. So eta equation coming here. So these are the parameters in quadrupole NMR. One is nothing but the quadrupole coupling constant CQ. CQ, nothing but the quadrupole coupling constant. CQ also I have written here. Yeah. This is nothing but the quadrupole coupling constant. I think better to write quadrupole coupling constant. Quadrupole coupling constant. CQ. So CQ is given by this expression. This eta asymmetric parameter is equation is there in the previous slide, and the gamma is called Sternheimer anti-shielding factor. So that is coming because of the electric field gradient, which is distorting the electron powder. Let us go further. This I will quickly discuss. There are two types of quadrupole interaction. One is first order and another is second order. And before going that, we have in the periodic table now, there are spin 1 nucleus. This is also quadrupolar nucleus. Then spin 3 by 2, spin 5 by 2. I don't know if you see in one of the slides previously I have shown, I think it may be here, I think. You see here, some of them are spin half. Some of them are half integer, but some of them have spin 1. That is why there are 31 spin half, 9 integer spin. Integer means what? I is equal to 1. Nitrogen, deuteron, I is equal to 1. 9 integer spin. And 18 spin greater than half, means half integer spin. So 18 nucleus have spin greater than half, or half integer nucleus. Half integer means 3 by 2, 5 by 2, etc. For example, deuteron, if you see, deuteron is having a spin of 1. So if you have a spin of 1, it will split like this, +1, 0, -1. So one quanta here, one quanta here. So these are the two transitions possible. So that is why in single crystal, we get 2 peaks, and if you have a powder pattern, we get all orientations, and we get a peak like this. So for the time being, forget about the expression. So this is valid for the quadrupolar nucleus, and omega 0 is the frequency for this one. Due to electric field gradient, there will be a plus omega q also, minus omega q also. This is why 2 omega q is coming here. So this is a straightforward concept which we are telling, that whenever you see only one type of environment, for example, if you have an isolated molecule of proton, then it should be like this actually. Nuclear transition, we should be able to clearly see. And another effect, spin half nucleus. Spin half nucleus, what happened? We have 2a plus 1. Well, no, not half, 3 by 2. For example, B11. It's a 3 by 2, spin 3 by 2. So we have got plus 3 by 2, plus half, and minus 3 by 2. Or you see 2a plus 1 level should be, it will split into 2a plus 1 level. So we have 4 levels possible. So transitions are possible in this way. And in principle, we should get this one. For single crystal, we should get like this, and powder pattern, we should get like this. And this transition we call it as a central transition. And this transition, these two transitions we call as satellite transitions. ST means satellite. Satellite transition. Satellite transition and central transitions. So this is the ideal case. I am just showing you to get a feeling of how a quadrupole. For a spin half nucleus, what happened? We will get only 1 peak. But for quadrupole nucleus, in the case of a spin 3 by 2, we should get 3 triplet if it's a single crystal, or if it's a powder pattern also, we will get a feature according to that. Let us move further. So these are all considering the first order quadrupolar effect. Then quadrupolar, these are all perturbations, because we have got a very high magnetic field, and first order quadrupolar perturb the nucleus, and then second order quadrupolar also perturb the nucleus. Second order quadrupolar you see here, that is because of the second. This can be calculated by perturbation theory. You can calculate how much is the distortion. We will not go into the details. This one important thing I want to convey is here. This central transition you see here, central transition is here. Correct, na? Central transition is not much affected by this plus half to minus half transition, is not much affected by this quadrupolar, first order quadrupolar interaction. You see here, it is getting affected here. Satellite transitions are getting affected. These are ST means satellite and CT means central. Central transitions are not much affected, but the satellite transitions are getting affected. But if you go for second order, both central as well as satellite transitions do get affected. That is what we see here. Now, how this first order and second order are depend upon the magnetic field. This is same concept only I am telling. For a 5 by 2 nucleus, it looks like this. But you will be able to, if you know 3 by 2 nucleus, how it will look like, 5 by 2 nucleus, you can equally write. Aluminum is an example of a 5 by 2 nucleus. So it's split into 6 level, 1, 2, 3, 4, 5, 6 levels. You can see here plus 5 by 2, plus 3 by 2. This is in the Zeeman, and this is because of the first order quadrupolar interaction. You always see the central transition is not affected by first order, but satellite transitions are affected. And of course, second order will be affected, all transitions will be affected. So total Hamiltonian will be whenever you write now, this is the Zeeman term, this is the chemical shift term, and then comes the quadrupolar, first order quadrupolar interaction, and second order quadrupolar interaction comes here. So these things I have explained, there are expressions, you need not remember that, just for your have a feeling of the subject I mentioned. But one very important thing I want to confirm here is that the first order transition, now you see here, there is an angular term called the 3 cos squared theta minus 1. First order, you see nu m is equal to 1, and first order term, there is a parameter called 3 cos squared theta minus 1. So if the magic angle, if the theta become magic angle 54.74 degree, cos squared theta will become 1 by 3, 3 into 1 by 3 will become 1, 1 minus 1 becomes 0, and the first order term will cancel. But if you go to the second order quadrupolar interaction, it is having a somewhat complicated angular dependence. That is 1 minus cos squared theta into tan cos squared theta minus 1. So it will not get averaged out. By doing magic angle spinning, it still remains that. These are the angular dependence. Then we have also magnetic field dependence. For example, HQ1, that first order quadrupolar term is proportional to CQ. Does not affect central transition, but second order is inversely proportional to the applied magnetic field. If you have very high magnetic field, then the second order can be removed. But it is having an angular term somewhat complicated compared to the first order. So normally the second order quadrupolar is a problem, second order quadrupolar interaction, because first order we can average it out by doing mass. So second order we need to take care. Normally if you take an NMR of quadrupolar nucleus, probably you will not get anything. It is very difficult to understand the spectrum. For example, because first order interaction, second order interaction, all of them will complicate, and then you have powder samples. In laboratory, you cannot get single crystal always. Getting a single crystal is very difficult. So normally you encounter with powder sample only. If you do a powder sample, static NMR will look like this one. Sodium, this is a sodium 23, Na23 mass NMR of sodium oxalate. Na2C2O4. Oxalic acid if you take, if you substitute 2 protons by sodium, you get the combo powder sample. And static NMR, you cannot get anything. See, these are something like you cannot get, it's a very broad peak. But if you do magic angle also, you see, you cannot do anything. Some sort of a distorted line shape. You see here some double splitting is there, very genuine or not, we don't know, very small splitting, and then there is a shoulder. Sometimes you are not able to also face properly. This region, there is another peak. So when you do mass or when you do static NMR, particularly when you do like sodium, because quadrupole coupling constants are quite high, it is difficult to get information. So that is why a new technique called a double angle rotation. We talked about magic angle spinning, correct? Now the magic angle spinning is only at a particular angle. Now, if you can manage in such a way, you can rotate in 2 angles. One way you can do is rotor axis time you change. If you change the rotor axis as a function of time, you see here, initially rotor axis was here. Now it will move here. It will move here. As a function of time, if you move, in fact, some of the interactions like second order quadrupolar interaction, you can average out. So that is called double rotation. You see here, I am changing the rotation axis as a function of time. So here only single rotor is there. Rotor means sample container, correct? Only one sample container is there. I only change the axis. This is somewhat cumbersome, but nowadays modern equipments are there in which you can change the axis of rotation periodically as a function of time. Another way is which is much more complicated called rotor rotation, 2 rotors. If you take one rotor in a small rotor and put it in a big rotor, and you rotate at different angles. So here 2 rotors are required. That is called a double rotation because you use 2 sample container. This is called dynamic angle spinning, called a dash. Dash means you keep on changing the rotation angle, axis of rotation. So once you do that, you can get a well-resolved signal. That is what I have shown here. This you may look into it. See, I have done a dynamic angles spinning NMR of a compound called the calcium silicate, Ca2SiO4. There is a mineral name called Larnite. This Larnite is having many peaks. 4 peaks are there. 4 oxygen peaks are there. By the way, oxygen 17 is a quadrupolar nucleus. It's a 3 by 2 string. So it is having 4 different oxygens are there. That can very well resolved by doing a DAS, dynamic angle spinning, or by doing a double angle rotation. Of course, double angle rotation appears to be more resolved, you can see here. So others are side bands. So you'll be able to find out by what is the chemically different. You can get a resolution, high resolution solid state NMR by doing this dynamic angle or double rotation NMR. Just to give a feeling of that, this compound I have already said, ALPO. ALPO is nothing but a molecular C. The commercial name is VPI5. It is nothing but aluminium phosphate. If you do mass, if you do an aluminium 27 of magic angle spinning NMR, you see how broad a line it is. Very, very broad. You cannot, it is extending from almost like a 28 ppm to almost like 40 ppm. However, if you do a double angle rotation, double rotation or dynamic, you are able to see second order quarter polar interaction get averaged out. You can see well distinct peaks because of this is a dehydrated sample. You can see aluminium with a different number of hydroxyl molecules. You see here this aluminium, which is characteristic of the tetrahedral aluminium, with a different amounts of water molecules present. This can be found out by this aluminium 27 mass NMR. And this is what dehydrated, there is no, if you do a dehydration, what happens? There is no ALOH species. The moment you start hydrating, then the ALOH species comes. And here if you see, hydrated for 2 days, you see so many signals have come of ALOH linkages. And 23 days you see lot of aluminium NMR signal you can see. These are all obtained by aluminium double resonance NMR. Double rotation, not double resonance, double rotation NMR. You use two rotors, get this information. By single rotor, you will get a broad peak like this. So you can get chemical information or the local environment around aluminium can be monitored, and we can get rid of the second order quadrupolar interaction to get a sharp lines from the aluminium species by doing DOR. The same example only I have given here, aluminium 27 of aluminium phosphate 21, another sample in which you can very well see the two peaks which are characteristic of the aluminium with the different chemical environments. So once you have the spectrum, you can always get the parameters like eta, then isotropic chemical shift values, quadrupole coupling constant, CQ values, etc. And then you see here aluminium 4. Aluminium 4 and aluminium 5, you see aluminium 4 is more symmetric, tetrahedral symmetry. The coupling constant is 3.7 megahertz. Whereas aluminium O5 is a distorted environment. So the coupling constant is 7.4. It's a distorted coordination environment. So the coupling constant also will give idea if it's a cubic symmetry or if it's a more symmetric, ALO4 is more symmetric, tetrahedral symmetry. So you can get a lower coupling constant. So coupling constant also give idea regarding the symmetry of the local environment. So aluminium, in many of the solid state NMR, many people have studied aluminium. Whenever the quadrupole coupling constant are large, you see patterns like this. This is due to first order quadrupolar interaction, and the second order also broad on the line shape. Basically the side band overlaps with the side band, then the picture will be something like this. So now let us give an example how aluminium NMR will be useful. These are some background of aluminium NMR or quadrupolar NMR I have discussed. How aluminium NMR will be useful for us. You might have studied in your solid state chemistry courses called, there is a compound called spinel. Some people say spinel, some people say spinel. Spinels are two types. Correct, na? One is called a normal spinel and another is called inverse spinel. One is called normal spinel, another is called inverse spinel. So what does it mean? What is normal spinel and what is inverse spinel? In normal spinel, A is at the tetrahedral site, correct na? Everybody will agree. And B is at the octahedral site. That is why I have written A is with the coordination number 4 and B is with the coordination number 6. So this is octahedral and this is tetrahedral. But the moment you go to inverse spinel, what happens? Part of the B goes to the tetrahedral site and all of the A or part of the A come to the octahedral site. Is it clear? So that is why I am writing here AB204. 4 is nothing but the coordination. 6 is nothing but the coordination. A is tetrahedrally coordinated, B is octahedrally coordinated. So part of the A is replaced by B and part of the B is replaced by A. That is why I have written B2 minus X AX and A1 minus X BX. So X is nothing but a parameter called inversion parameter. Correct, na? Higher the value of X. If the X is higher, what happens? If the, let us say X is 1, then A is 0 here. All the A is here only. It's a completely enough inverse spinel, 100% inverse spinel. Correct, na? If X is equal to 1. If X is equal to 0.5, what happens? Part of the A is here, part of the A is here. Part of the A is in the tetrahedral side, part of the A is in the octahedral side. So it's 50-50 spinel. Complete, not a completely inverse spinel. So X is a parameter which decides the spinel. Correct, na? R is nothing but the ratio of the tetrahedral and octahedral side. So now let us move further. Aluminium 27 NMR can be very well used to find out the Aluminium-27 NMR can be very well used to find out the concentration of aluminium in tetrahedral site and the concentration of aluminium in the octahedral site. For example, you see here the aluminium-27 spectra of a compound, magnesium aluminium. Here, you see here aluminium is tetrahedral site. You see in the small peak. Then there is an aluminium at the octahedral site. So if you take the ratio, what you will get is an inversion parameter X. Correct? So from the aluminium, you can, as a function of temperature, so if you increase the temperature, what happens? Part of the aluminium from the tetrahedral site will go to octahedral site, or octahedral go to tetrahedral site. There is an inversion happen. So X value should be different. So X can be easily calculated. And this can be plotted as a function of temperature. So X value increases, means more and more inverse spinel structure is coming when you go from, if you increase the temperature. Another very important aspects of NMR, aluminium NMR. See, in aluminium NMR, you want to find out how many aluminium is in the tetrahedral site and how many aluminium is in the octahedral site. Only one possibility is there. What is the possibility to an NMR? Because NMR will give a parameter of tetrahedral. It's a peak corresponding to ALO4 and peak corresponding to ALO6 structural unit. So from that you can calculate how many aluminiums are in the tetrahedral site and how many aluminiums are in the octahedral site. Consider a compound called gamma alumina. Gamma alumina is a very interesting compound. It is used as a ceramic material for various applications. It's a defective structure. It is used in solid state electrolytes and all. See, gamma alumina can be mentioned like this: aluminium 2 4 by 3 into aluminium 3 4 by 3. Correct, na? Because it is 8 by 3, this is 12 by 3. So it is nothing but Al2O3 only. This is Al2O3. I have just changed the formula. Correct, na? 2 I have multiplied with the instead 2 I multiplied with 4 by 3 and 3 also I multiplied with 4 by 3. So nothing is going to change. So effectively you will get Al 8 by 3 and O4. This I am trying to correlate because we have got MgAl2O4 structure. Na? So that is why I am writing this AlO4. O4 is coming. So Al 8 by 3 can be always written as Al 2 by 3 Al2. So this aluminium is in octahedral site, whereas this aluminium is in tetrahedral site. So by doing the NMR, you can find out how many aluminiums are on the tetrahedral site and how many aluminiums are on the octahedral site. So any person, suppose you are giving a gamma alumina, you can calibrate the NMR. Suppose I want to calibrate the NMR. I know what is the aluminium percent in the gamma alumina. So what I will do, I will take this gamma alumina and record an aluminium NMR and get the ratio of tetrahedral peak and octahedral peak and say how many aluminium tetrahedral and how many aluminium octahedral. Now if I take any unknown compound, unknown spinel, so from the relative intensity of these two peaks, I will be able to find out how many will be in the tetrahedral site and how many will be in the octahedral site. So this will be helping us to do the cation distribution, because many times cation distribution is important aspect to predict the properties of the material. So cation distribution can be understood by recording the aluminium-27 mass NMR. Similarly, boron is a very important nucleus for us. Most of the glasses are basically borosilicate glasses. Borosilicate glasses are very widely used in DAE for different applications. We will not discuss all those things. As I mentioned earlier, now boron is having two stable isotopes, non-radioactive stable isotope. One is B10, which is having a spin of 3, and another is B11, which is having a spin of 3 by 2. B11 is a very good system. It's a spin means a quadrupolar nuclei only, half integer quadrupolar nucleus. If you take boron, now boron is having a very interesting structure. See, boron here 1, 2, 3, 4 coordinated boron. But here what is that? Boron is having 3 coordination. Similarly, here boron is having 4 coordination. Here boron is having 3 coordination. So in borax structure, theoretically, we have 50% trigonally coordinated boron and we have 50% tetrahedrally coordinated boron. Am I right? Correct, na? Because this is the two borons are tetrahedrally coordinated and two borons are trigonally coordinated and 2 borons are tetrahedrally coordinated. This is a B minus because there is a 2 sodium ion also will be coming because this is a B minus. So 2 sodium has to there to neutralize the charge. But interesting thing is that although I say in the structure there are 2 boron in tetrahedral and 2 boron in trigonal configuration, you see the chemical, you see the intensity pattern. boron. This is B. B means nothing but 3-coordinated boron. And A is nothing but 4-coordinated boron. If you take the relative intensity, then it should be 1:1. We are not getting 1:1. Is it now? So there is a detector sensitivity for the tetrahedral boron is somewhat lower compared to that of the the detector sensitivity for the trigonal boron is somewhat lower compared to that of the tetrahedral boron. That is why we get a lesser intensity peak for boron in trigonal configuration compared to boron in tetrahedral configuration. In fact, you need to calibrate the machine. When you do an B11 NMR, we need to calibrate. So that for then only you'll be able to calculate the unknown sample, how many boron is in tetrahedral and how many borons in octahedral. We need to calibrate the system before doing the NMR. So this is very important. Another aspect is that why this is coming around 15 ppm and BO4 is coming around 0 ppm. Because boron in 3-coordinated, what happened? We have only 3 oxygens. So 3 oxygen means electron density is given by only 3 oxygens. So electron density is less here. Whereas boron in 4 coordination, if you see, is coordinated with 4 oxygen, 1, 2, 3, 4. So the electron density around boron is more here. So when the electron density is more, it is shielded more. That is why we get a lower chemical shift value for the BO4 structural unit and a higher chemical shift value for the BO3 structural unit. Hope these things are clear to you. So directly you cannot take, you will not be able to take from the NMR spectrum exact value of BO3 and BO4 from the spectrum. You need to calibrate the spectrum. You need to run the standard and see how much is the detector efficiency for the boron 3 and boron 4. Then you can calculate the boron 3 and boron from unknown samples. So typically you see the boron NMR BO4, which is nothing but the tetrahedrali coordinated boron, is having a relatively sharp peak and it is more intense compared to boron in a trigonal configuration. You can see here the intensity is very weak. But one more thing you can see, why you can see one more thing, you see here BO3 and BO3, this top, the blue color NMR, blue color pattern is taken with a magnetic field of 18.8 Tesla. Means 18.8 Tesla means almost like 800 megahertz NMR machine. 800 megahertz means what? In that machine, the proton frequency is 800 megahertz. 9.4 Tesla means what? 9.4 Tesla means the machine is 400 megahertz machine. 400 megahertz machine means we have a proton signal which is having a frequency of 400 megahertz. So I changed the magnetic field. I recorded the sample in 2 different magnetic fields. One is at 9.4 Tesla magnetic field, another at 18.8 Tesla. I see well-refined peak. In the case of 400 megahertz machine, you see that tetrahedral peak is tetrahedral peak is seen, but the trigonal peak is not clearly seen. The moment you go to double the magnetic field, you will very clearly see the well-resolved trigonal peak. Why we see that peak? Because if you see this expression, quadrupole coupling constant, second order quadrupole coupling constant is inversely proportional to omega nu zero. Nu zero is nothing but omega zero. Omega zero is nothing but Lamarck frequency that is directly proportional to the magnetic field. So higher the nu zero, higher will be the magnetic field. So if you have higher magnetic field, then the Q2 term will be very less. So that is why we are able to see well-resolved peaks for B11 NMR in this spectrum. Hope things are clear to you. So when we try to do a B11 mass NMR spectrum of borosilicate glasses. The typical B11 mass NMR spectrum of borosilicate glasses is shown here. BO3 and BO4. These are the structural units we can very well see. These BO4 and BO3 structural units are related to the network, glass network. And from this we can predict the properties of the glass. So in glasses there is something called a boron anomaly. This boron anomaly is nothing but with a change in the boron concentration, there is a change in the thermophysical properties of the glass. And that thermophysical properties of the glass is brought about by the relative changes in the BO3 and BO4 configuration. And this can be easily monitored with the help of a B11 mass NMR. So that is the purpose of doing this NMR. So you can also see the moment you add alumina in borosilicate glasses, let us see how the spectrum is looking. If you don't add any alumina, you can see the concentration of BO3 is not that high. But addition of alumina, you see some of the B2 or 3, BO4 structural unit get converted into trigonally coordinated boron. Some of the BO4 structural units are getting converted to the some of the BO4 structural units are getting converted to the BO3 structural unit. You see here the top peak, which is 0% aluminum and 15% aluminum. You can see the peak which is developing at around 15 or 14 ppm, and this broad peak is due to boron in trigonal coordination. So the additives in the glass or anywhere, if you use any material, if you do additives or use some different components to modify the structure, the boron NMR changes. So one can monitor the boron NMR by doing this B11 mass NMR. It will be very difficult because boron is a low Z element. Once you go low Z elements, diffraction techniques fails, particularly X-ray diffraction, etc. So one need to go really NMR technique only to understand the relative changes in the boron environment occurring in any material. So let us give somewhat more better good idea. So what more information you can get by doing NMR of quadrupolar nucleus. Probably this I have taught you in the previous, I think maybe 2-3 lectures back. There are single quantum, zero quantum, and there are double quantum. Is it not? In the case of a phosphorus nucleus, in a phosphorus glass, I explained to you how a DQ NMR. What is DQ NMR? DQ NMR is simple, it is nothing but double quantum NMR. How a double quantum NMR can give information regarding the coupling constant. Probably you see the literature or you see the notes or you see the slides, any doubts are there, you can write to me or you can contact me. But double quantum NMR is an ideal technique to monitor the dipole-dipole coupling. But this double quantum metal I told for a spin half nucleus like phosphorus 31, is it not? I solved you for the glass sample PbO P2O5 or Na2P2O5 glasses where phosphorus is spin half nucleus. Whereas in the case of a quadruple nucleus, we have MQ mass. What is MQ mass? MQ mass is not double quantum, multiple quantum. Multiple quantum transitions are possible. So same principle, you apply a pulse, then wait for some time, then do another pulse, and then monitor the acquisition. That is the same principle only. Only thing is pulse power or pulse duration, etc. can be different. Let us move further. See in this case now. See you have a 0 here, +1, +2, +3. See first quantum, second quantum, and third quantum here. First quantum here, second quantum here, third quantum here. Here also first quantum, second quantum. This is nothing but a 3Q. Triple quantum NMR experiment, triple quantum, because 3 quantas are involved, and 3 quantas we need to apply sufficiently high power so that this triple quantum transitions can be made operational. Otherwise, it is very difficult to get triple quantum transition with a normal power, normal pulse powers. By using high power pulses, you can have a triple quantum transition and monitor this triple quantum transition against a mass means magic angle dimension transitions. Single quantum transition. Of course, you can say triple quantum versus single quantum transitions monitoring can be done. So that is what we do here. See, if you do, it is very difficult to distinguish between a oxygen 17 NMR using SiO-Si and ALO-Si. Of course, there is a feature is seen. Normally, you get like a broad peak. If you make an aluminosilicate NMR, oxygen 17 NMR, you get a broad peak like this. And this broad peak is because of the silicon. 2 types of bridging oxygen. One is SiO-Si and another is SiO, ALO-Si. If you do single pulse mass, again that information you will get a small folder, and from that very difficult to find out which is which or what is the structural units. So in such cases, if you use a multi-quantum NMR or a triple quantum NMR or O17 multiple quantum NMR, you will be able to, in 2 dimensions, you will be able to see a very well resolved peaks for SiO-Si and SiO-Al linkages. SiO-SL or SiO-Al linkages. Similarly, in glass samples, oxygen 17 MQ mass is nothing but multi-quantum magic angle spinning NMR is very widely used to understand different types of bridging oxygen atom. Because in glass, what happened? We have sodium borosilicate glass, we have SiO minus, Na plus, which is nothing but the non-bridging oxygen. Then we have got a bridging oxygen. Then we have an SiOB linkages. All these linkages can be easily distinguished with the help of a multi-quantum NMR technique. Normal NMR, if you see here, now you will get a broad peak like this, and there is a slight asymmetry only you can see. And from this, very difficult to get information. What are the type of silicon or a silicon structural unit, oxygen structural unit present. So that is why this is also in number magic angle spinning. So you cannot get much information. Whereas by doing an NQ-MOS, by applying high pulses and then plot MQ-MOS NMR. Here what happened, two axes are there. One is nothing but the mass dimensions, which is nothing but the normal this dimension. And another is nothing but the isotropic dimension due to the triple quantum effect, triple quantum NMR transmission. Because you are applying a two-pulse sequence. Correct now? You are applying a two-pulse sequence. If you apply very, very strong pulse, what happens in this region, the triple quantum spin resolution, spin evolves. And this coherence of the spin evolves, and this can be monitored indirectly in this time window. So what you get is nothing but you are having three different types of bridging oxygen. One is nothing but the SiO-Si, another is SiO-B, and there is a non-bridging oxygen atom. I think I will conclude with this slide. There is another very versatile technique has come recently over the last 5-10 years. That is called combined rotation and multiple sequence. That is called cramps. By using the notation cramps, it involves combined rotation also, multiple sequence also. That way you can get proton NMR. Because the proton NMR, now if you take a proton NMR, that will be very, very broad. Because the coupling constants are very, very high. You see here, if you see a static NMR pattern, it spreads like anything. It comes from almost like 42, plus 42, minus 40 ppm. No information can be obtained. Even if you spin to very high spinning speed, then also you will get a distorted line shape. Or line shape which are difficult to interpret. You see here, distorted patterns you will get. I think if I have pulse diagram, anyway, pulse program I have not, or pulse diagram I have not shown. But this process, there's a pulse program called continuous rotation and multiple. You apply a pulse and then you multiply pulse. Multiple pulses you apply in one rotational period. And as a result of this, what you do, you get rid of the dipole-dipole interaction. Once you get rid of the dipole-dipole interaction, you can see the well-defined peaks. For example, in the case of adipic acid, what happened? We have protons, different types of protons you can see. By doing cramps, you can see different types of protons. Let me continue further. So this is one versatile technique which is widely used for understanding the biomolecules or proteins, etc. The material called the technique called the cramps that is used in proton NMR technique and the proton solid-state NMR. Proton solid-state NMR people were not using, but over the period of time, due to the evolution of the due to the discovery of new pulse sequence, people are able to design experiments in which we can get rid of the strong dipole-dipole coupling and we can get well-resolved proton NMR spectrum from the inorganic compounds. So that is what the advantage which I have shown here. So this probably you will be able to understand this aspect. So I think I will stop here. If you have any doubt, you mail me. Some more topics are there in saying how the boron NMR changes, boron anomaly, how the chemical variation and all those, how you can study the relaxation times to correlate the molecular motions, etc. Probably I think we will not cover this. So probably for examination, these 12 lectures only, I will stop here at this point. So we go through all the slides, and in case any doubts, kindly mail me. I will be happy to answer, or I can discuss also maybe sometime in a free time I can discuss.
Yeah, and ask to submit the.
And also kindly submit the assignment. Assignment carries some marks. So kindly submit the assignment. It's very simple. At any time you have doubt or you want clarification, you can mail me. I can help you to solve the problems. And the assignment carries some marks. You can easily get that marks. Already one person has submitted also. So kindly submit the assignments. And please go through all the slides. In case any doubts are there or any clarification is there, mail me. I'll be happy to answer. So with this, I may close.
For today's presentation, any doubt? You can just write.
Nobody else actually.
YouTube.
Huh?
In YouTube, there are 3
Any doubt, you just write. I think no response.
Hmm.
Okay, if no doubt, then we stop it here today. And this is the last class from Professor Sudarshan's side. So any doubt, you can directly write to him, or you can email to our HBNI site. All right. And our next class will be by Professor Hushio. It will be on Wednesday at 3:30. Okay. All the
So
best.
with this, all the best. Thank you very much for attending all the classes.